Today's goal is to define a sequence or a series. Well, what is a sequence? A sequence is a list of numbers. For example, 1, 2, 3, 4, and so on. These ellipses, the dot, 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 indicates that the sequence goes on forever. We'll talk about series in a minute. Let's look at example 1. List the first terms, let's say the first 5 terms of the sequence f of n equals 5.2 plus 1.6n, where n is greater than or equal to 0. This is a sequence given in explicit form. An explicit form means that you can calculate any term in the sequence simply by substituting into n. This is the domain of the explicit sequence, and it tells us which value we should substitute in first. So that's like saying, if we want to find the first term in the sequence, we first substitute in 0. So we would have 5.2 plus 1.6 times 0 would be our first term, f of 0. Of course, we get 5.2. The next term is going to be some n value greater than 0, since we already did the n value equal to 0. So f of 1 is 5.2 plus 1.6 times 1. So 5.2 plus 1.6, 6.8. Now, of course, I'm going to find the next term, and the next term, and the next term until I have 1, 2, 3, 4, 5 terms, right? The initial term plus an additional 4 makes 5 terms. When I said explicit, though, I could find them out of order. If I wanted to find term f of 4, all I'm going to do is use the same formula and substitute 4 into the equation. Calculator. So this term would be 11.6. I could find them again out of order. Okay. So this sequence would look like 5.2, 6.8, 8.4, 11.6, and so on. I'm putting the dot, dot, dot in there, those ellipses. That's an English language arts term for it, to indicate that these are only the first 5 terms, the initial, and 4 more, but then the sequence would keep going. It's just an infinite list of numbers. Okay. Example 2. List the first 5 terms of the sequence f of n equals 5.2 plus 1.6n, where n is greater than or equal to 1. Again, this is an explicit definition of the sequence. It's almost identical to our other sequence, except this time we're not allowed to start by subbing in 0. We have to start by subbing in 1. Well, we already know that f of 1 is 6.8, and f of 2, and f of 3, and f of 4 we already know. This time we'll have to find f of 5. We substitute, and you get 13.2. So here my first 5 terms are 6.8, 8.4, 10, 11.6, and 13.2, and so on. All right, let's take a look at another example. List the first, let's say, 4 terms of the sequence f of n plus 1 equals f of n minus 3 and f of 0 is 2. Now, this is a different way to define a sequence. There are two ways to define a sequence. One way is explicitly, one way is recursively. This is a recursive definition. And I'm going to show you what that means in a second. Okay, the first four terms, they have to give you the initial term. F of 0 is 2. So I've got one term listed. Now, this notation means the next term can be found by taking the last term, the previous term, and subtracting 3 from it. So I'm going to take the previous term, 2, and just subtract 3. Get negative 1. Okay, so then the next term, again, I'm taking the next term will be the last one. This time my last one is negative 1, and I subtract 3. So my previous term, subtract 3, I get negative 4. My next term, I take the last term, subtract 3, and I get negative 7. Here are my first four terms, an initial and 3 additional terms, 2, negative 1, negative 4, negative 7, and so on. The biggest difference between a recursive definition for a sequence and an explicit is that if, for example, I wanted to find f of 5 for this one, in order to find the next term, I'd have to know the previous term. I can't find f of 5 without knowing f of 4. And to find f of 4, I have to know f of 3. Here, I could skip around. I found f of 4 before I found f of 2. I can find any term in any order, but a recursive definition requires you to know the previous term in order to find the next term. Okay, let's take a look at another example. This one will be a little different. Define this sequence recursively and explicitly. And here's my sequence. It's given as a graph. The first coordinate pair is 1, 2. The next is 2, 4. The next term is 3, 8. Run out of room. And so on. Okay. To define it recursively, that means in order to know the next term, you're doing something to the previous term. And you gotta say what your initial term is so you know where to get started. Well, the initial term, in this case we're using the x value 1, is the first point we see. So we'll call it f of 1. The initial term will be 2. You could think of this as being the index, or like which term you're calling it, and these would be the actual terms in the sequence. Okay. To get the next term, to get from 2 to 4, I'm multiplying by 2. To get from 4 to 8, I'm multiplying by 2. So I'm taking the previous term, I'm multiplying it by 2 to get the next term. Here's my recursive definition. Explicitly, I know multiplying by 2, that should look like an exponential function. I'm thinking a times b to the x power. Oh, well, my initial value is 2. To get from 2 to 4 and 4 to 8, I'm growing by a factor of 2, so it would look like 2 times 2 to the, oops, we use n because we're only substituting whole numbers in, just as an aside. And I'm starting where n is greater than, ooh, this is tricky. I want my first index to be 1, but then I'd have to think, if I went backwards in time, it would have the y value 1 if I was allowed to use the x value 0. So let's change our initial value. It would have been 1, but we're starting by substituting in 1. Let's just double check. F of 1, the first thing I'm allowed to substitute, would look like 1 times 2 to the first power, which is 2. The next thing I'm allowed to substitute would be 2. Oh, yeah, this is the right pattern. Here's my explicit definition. Okay, now that's enough about sequences, which are, again, these infinite lists of numbers. Let's talk about series. A series is a sum of terms, meaning you're taking a bunch of stuff and you're adding it up. Let's do an example. Sometimes you're asked to evaluate a sum. Evaluate, of course, means find the value the number is equal to. Let's evaluate this sum. You see the Greek letter sigma, so it would be the sum of the terms, 5.6 times 2.3 to the n power, where n goes from 0 to 11. Now, there are two ways to do this. The first strategy would be do it by hand. What this sum means, this sum would say first substitute 0 in for n. So we'd have 5.6 times 2.3 to the 0. Then sigma means add. Then you're substituting in 1, 2, 3, 4, all the way up to 11. So we'd substitute 5.6 times 2.3 to the 1 plus 5.6 times 2.3 squared plus 5.6 times 2.3 cubed plus blah, blah, blah. You'd have to keep adding up. Your last one would be 5.6 times 2.3 to the 11th power. It's going to take forever to type in your calculator. So luckily there are a few strategies you can use on your calculator. Okay, please listen to the part that corresponds to the calculator you own. If you have an 84 plus, TI 84 plus, you're looking for the sum function. So I would suggest, unless you remember where this is, there's a handy tool called Catalog, which has a catalog, a list of all of your functions. So press the blue button to get there. It pulls up a list. You're looking for the sum function, so you can look for the letter S. Oh, that would be right here. I'm going to press S. It just scrolls down. Now you got to find the sum function. Summation. Look for that sigma. How nice is that? This looks exactly like the expression you were given. You're just going to type in values. Now, this expression has n's, but you can use x instead, right here. So you have x going from 0, to 11. And you want 5.6 times 2.3. Those are parentheses to the x power. Just make sure your variables match whatever you decide to use. Oh, this is so nice. It did all the math for us. So our sum would be 94,397.1514. That's it. You didn't have to show any work. You could say, use my calculator to find the sum or the value of this expression. Okay, if you have an 83, it's going to be a different strategy. Let's take a look. This is a little bit tricky to do. So we're going to look for, again, go to Catalog. Again, press S. Now, you're going to have to do this in two parts. You want the sum. It doesn't have an option for you with sigma. So press the sum. Now go back to your catalog. Go back to S. You're going to do the sum of terms in the sequence. Because you're just adding up terms in a list, right, that follow this pattern. Choose the sequence with the parentheses. Now you got to say what the sequence looks like. The sequence looks like 5.6 times 2.3 to the x power, where you're using the variable x, so use comma, it's right above 7. So 5.6 times 2.3 to the x, comma, 0, comma, 11. That means here's what we're calling our sequence terms. Here's what they look like, where we use the variable x from 0 to 11. Good, you get the same answer no matter which calculator you use. That is good. If you're using an Inspire, go to calculate. Spoiler alert, there's the answer. Press menu. Choose option 4, sorry about this, which is calculus. Then choose sum. Again, it's bringing up a template that you can type into. I like to use the variable x, but if you want to use n or whatever, it doesn't really matter. Type in your values. And press enter. Sorry, it's hard to see. And there's your answer, there's your sum. It just run it for you. Okay, one more question, and then we'll be done with sequences and series. 5. Oops, example 6. Let's evaluate this series. Series again means a list of terms you're adding, not just listing them. The dot 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 plus means the same pattern continues. Assume the same pattern continues until the last number you're adding up would be 60.6. Okay, I know that it's really quick to evaluate if I have a calculator. So I want to put this series in summation notation, also called sigma notation. Sigma is that Greek letter. So I gotta know what the pattern is so I know what my terms look like. So I gotta see, am I multiplying, am I adding? Maybe I try adding. To go backwards, of course, you subtract. Oh, good, the pattern holds. I can just add 3.4 each time, and then the pattern will continue. So my summation notation, or sigma notation, it's gonna look like mx plus b, right, a line. It's 2.8 plus 3.4n. Just adding 3.4 and then add 3.4 again, and blah, blah, blah. Where n equals 0, I could call this my initial term. N goes from 0 to something. Well, 60.6 is some term in this sequence, so it'll look like 2.8 plus 3.4n for some n. So I can solve this equation. I have 57.8 is 3.4n, and is 17. So I'm saying this would be the initial term, 70, yep, checks out. This would be the next term, 2.8 plus 3.4 times 1, yep, is 6.2. This would be the term after that. This would be the 17th term after the initial term. So I'm saying the terms go from the initial up to 17 more. Well, my goal was evaluate, get a value, a number. So I need this to all be worth one number. I'm going to type it into my calculator using my same strategy from above. I find that the value is 570.6. Make sure you can do that on your calculator.